Good afternoon to everybody. Dr. Maiti sir, I will start the session now. Okay, sir. Before going our regular practice, we can have the voice test so that I will come to know whether voice of speaker is audible or not. In this 5 days FDP, we have seen from the fiber to garments. What are the processes are there, and what are the instruments or devices going to be used, how the testing of the fabric is going to be carried out. This is the combination of so many courses. If you are talking about textile engineering, then this is going to be more than undergraduate course, which we are trying to cover within a 5 days. We have given the glimpses of all these things, and you are able to understand the importance of your branch also. Now the special project which Mantra and SVNIT is doing collaboratively for the Stenter machine in the industry, in that work I am going to share with you. Please participate in the vote. Around 40% participants voted. Please fast. About 40% only given the vote. Remaining all of you participate in that. Be fast so that we can start the lecture and we can finish in a time. This poll is going to be open for next 30 seconds. Be fast. If there is any difficulty in listening to the voice, I request you to check your audio setting or leave the meeting and rejoin it back. Please vote. Those who are not given the vote, please. If you are not able to see the poll on your screen, move the screen right side or left side, and again bring it back. The screen is going to be visible. Then poll it appropriately. I think 50% people are only voted. Last session, only 50%. It is not encouraging. Remembering all of you have to vote. All the participants be attentive. All the participants be attentive and vote in that. I'm closing this within a 5 now. I'm going to close it now. Okay, around 95% are able to listen the voice of the presenter. It is audible, and those who are not, I request them again to check the audio system. Hopefully my screen is also visible to you. Okay, Dr. Mehdi sir, I will start the presentation.
Yes, sir. Yes, sir.
Yeah. Okay, sir. As already I told you, this particularly the project titled Energy Model Based Benchmarking of the Stenter machine used in the textile industry, not only for the drawing but other applications that we are going to discuss more in detail. This work is combinedly done by the SVNIT and Mantra. This is a sponsored project we got from the Ministry of Textile. This is the SVNIT campus, very green, 250 acres. Once the situation is going to be normal, we are going to conduct the programs over here physically also. At that time, we'll definitely invite you also. Please visit the campus whenever it is possible, and if you are close to the Surat or any way you are coming to the Surat, please let us know. We'll help you to arrange the visit to the SVNIT. Definitely. Basically, being a National Institute of Technology, its involvement is in various teaching, research, and testing and consultancy. About the mechanical department, we have the BTech, MTech, and PhD degree. Research and development in that various areas are there. Out of that, energy efficiency management, environmental issues, renewable energy, solar, small hydro, consultancy and testing. We do part in the energy audit, hydrodynamic systems.
Sir, Bade sir.
Yes sir.
Sir, मैं संजय बोल रहा हूँ.
हाँ संजय बोलो.
सर पीपीटी विजिबल नहीं हो रहा है आपको शायद.
तुम्हें स्क्रीन आगे पीछे करना पड़ेगा.
अच्छा ऐसा कुछ है.
हाँ, it is your problem or participants are saying?
सर मुझे क्विक पोल दिख रहा है इसलिए मैंने आपको मैसेज किया.
नहीं बहुत कम स्टूडेंट पार्टिसिपेंट्स को वो थोड़ा सा स्क्रीन रेड हो जाता है ना.
Also they are seeing the quick poll.
हाँ सर, we are seeing in screen से quick poll show.
What is?
Quick poll.
Please change the screen sharing option.
Oh, sorry. I think I have not hide the poll. Yeah,
yes,
sorry.
Yes, sir.
Now it
is visible.
Yeah.
Oh, yes.
Yes. Sorry. Hopefully the screen is now visible. If there's any problem, you can make it in a question box. Question box is accessible to me, so I can see your comments also. Okay, just discussing about the special mechanical department, what is the activities it's involved. Then overview of the today's presentation. I will introduce about the Stenter machine, then move towards the energy model of the Stenter machine, then literature problem as a case study, what we have taken it. Then I will discuss about the field study of Stenter machine. For that, what are instruments used and data collection. Then I will go to the results, whatever we have got it in a discussion with that. And at the end, we can have the concluding remark. Remember here, in the modern era of garments of its own preference, garments basically is not only used as a need, but nowadays it is the fashion, and in addition to the fashion, it is also a protection in various ways. So garments is not remain just a basic need. Textile industry, if you are talking about as a whole, then in India's concern, it is a second largest employment generation, as well as the second export industry in the world's statistic. So from the economic point of view, also being a second exporter to the world, it is also important, as it is said that after the agriculture employment to over 45 million directly and 60 million people indirectly, approximately 5% of the share of GDP, then 14% to overall index of industrial production, contributing 11% to the country's export. Surat cluster, if you are talking about, then there are around 450 dyeing and printing units. Drying cost is around 12% of the manufacturing cost. And if you see the drying and printing houses over here, dyeing houses basically it's more or less conventional. And being a conventional, there are so many issues. To require the upgradation required a funding, and being a small scale or medium scale industry, much funding is not available. So there is no much research also happening in that, and upgradation is also not there. And being upgradation is not there, energy consumption is going to be very high. When we have seen these issues, then we said that we thought of let us try to analyze the energy intensive devices in the textile industry. Being a textile industry is an important industry from the Surat city as such. Surat is one of the textile cluster in India, basically for the man-made fabric. Man-made fabric, which is basically manufactured from the polymers, which is getting from the crude oil. Ultimately, it is a petroleum product. Then we're going to discuss about the energy model based benchmarking for the Stenter. Okay, benchmark data available based on the statistical benchmarking in the literature. If you see that the data, whatever is related or given over here for the Stenter, it is based on the statistical tool. So the drying process, if you are talking about poly sector, it varies from 2.5 to 7.5 gigajoule per TE. Then per tons of fabric. Then heat setting, it is 4 to 9, the same unit. And then drying and heat setting for the Surat cluster, it is going to be around 0.019 kilowatt hours per meter. So these units are different, and this is basically the average specific energy consumption. And it is not going to give you the idea whether my Stenter is efficiently working or not. For the particular process, how much amount of really the energy is required. If you are considering the first case, the drying, then energy consumption varies from 2.5 to 7.5. And if the Stenter, which I am using in this particular industry, is having energy consumption 5 gigajoule per tons, then what can I conclude from it? Whether it is going to be the energy efficient, or there is the scope of performance improvement, or whatever is going on, it's according to the best practice I am following it. No idea I am going to get from this data, right? Because this is basically depends upon the statistical benchmarking. Statistical benchmarking is also having other drawbacks, such as the life of the plant, then maintenance issue, maintenance, how well you have maintained the plant, then the operational skills. So all these affects on the energy consumption of the Stenter machine, and ultimately the benchmark data. Which segment of the Stenter machines you are considering, how old Stenter machines are there, how well it is operated, how well it is maintained, all these matters. If you are talking about the sector which is basically the small scale and medium scale, definitely these are the issues, and there we wanted to know how much exactly the energy consumption is going to be there, and this is going to be very clear from the energy model based benchmarking. Energy model is a recent tool for the any system to understand how the energy is flowing in that particular system, and whether from the energy point of view there is a possibility of performance improvement or not, right? So we try to identify the problems basically in the Stenter machines. Different make of the Stenter machines are used for the drying of different fabrics having variation in energy requirement. Few machines are old, few are latest, results in difference in the energy consumption for the same fabric. To reduce energy consumption, it is required to estimate minimum required energy consumption or the specific energy consumption. and compare it with the existing energy consumption. The difference shows the accessibility of the possibility of reducing the energy consumption. Energy input given in the Stenter machine is based on the past or experience without consideration of the optimal energy requirement to change the process and or geometric parameters for increase of the production or any other reason. Energy optimization is not considered to increase the heat transfer to the fabric from the moist hot air with temperature and fabric speed. Air velocity also plays the key role. So optimization is required. So these are certain issues which can be need to be addressed appropriately. Now we have not addressed all the issues, but we have taken some of them. In this presentation, I am talking mainly on the energy model based benchmarking. The energy benchmarking is the process of collecting, analyzing, and relating energy performance data of comparable activities with the purpose of evaluating and comparing performance between or within entities. Entities can include process, buildings, or companies. So this is the broader definition of energy model-based benchmarking. Energy model-based benchmarking is estimated based on the mass and energy balance equations. Remember here, the model, whatever we are using over here, it is basically based on the thermodynamics laws and energy conservation law, the mass conservation law. Mass conservation law is already everybody aware of it. Mass is conserved unless and until there is a nuclear effect. If nuclear effect is not there, then definitely mass is going to be conserved. And similarly, the energy conservation is also going to be happen as per the thermodynamic law. Theoretical specific energy consumption is calculated by considering the required energy for the process and various heat losses. Actual energy consumption is compared with the theoretical specific energy consumption by considering various parameters of the process in Stenter machine, irrespective of the machines. Before directly going to the Stenter, this particular case, what I will suggest is I will go to the I will show you some video related to the Stenter machine. So that you are going to get the idea. Yesterday also you have seen the video, but still I will also this is the inlet side of the Stenter machine. Hopefully I am audible, right? Voice is not going to be there as background, so I'm going to tell you the explanation. This is some dyeing agent required during the I think sizing and cleaning agent over here. Basically, this is the drying operation. The fabric is gray fabric, and they wanted to clean it, and after cleaning, they wanted to dry it, so that the printing is going to be taking place on this as per the requirement. So this is going to be dipped into the some chemicals, and afterward there is a mangling operation. Mangles are also shown, and this I will go back, and these are the mangling operation. 3 rollers are there, and through that it is pressed. So some amount of water is going to be removed, and because of that, drying load is going to be reduced. Then fabric is passed
video is not visible.
appropriately through the Stenter machine. This is what are shown is the control frame where the operator is going to be there. Right and left side there is going to be control panels of it, and the center portion is a feeding part. This is the inlet of the Stenter machine. This is the parameters shown over here, mainly the Stenter speed and the temperature of the chamber, hot air temperature of the chamber. There are
video is not visible.
Screens, and this is, I think, the semi-automatic Indian-made type of Stenter. Sorry, I just trying to show the video, and in that I forgot to share the screen back. I will go back again and to show the. This is the inlet side of the Stenter machine. Now it is visible, I think so. Okay, it is now visible. This is the mangle. These 3 mangles are going to be there, and through that fabric which is wet is going to be pressed, and some amount of water is going to be removed from it. This is the rollers, and through that fabric is going to be squeezed to remove the water content, which reduces the load in the Stenter machine. Then this is going to be the controlling frame of the Stenter machine. From that, the span of the fabric as well as speed, temperature, and all that is going to be controlled. These are the control panels on both the sides, and at the center there is going to be a feed of the fabric. Fabric is pinned on both the sides so that there is no sagging of the fabric, and it is always tried to keep in the particular tension to adjust its size. Best remember here, the Stenter is not only used for the drying operation, but it is used for the sizing and desizing. Sizing, desizing means the dimensions of the fabric are going to be set in the Stenter machine. In that, you can increase the size of the fabric or you can reduce the size of the fabric within a permissible limit. Further, after the coloring, for the fixing of the color or dyes, also the Stenter machine is used. So Stenter machine basically is having a lot of applications, and without the Stenter machine, dyeing and printing houses cannot exist. However, it is also an energy consuming device. This is the inlet of the fabric, and there are going to be number of chambers depending upon type of fabric. The chamber consists of dedicated heat exchanger, hot oil heat exchanger. We are going to see what is going to be the content in one chamber. This is going to be the motor for the blower, which is used to recirculate the hot air. This is again another motor, electric motor connected to the blower, circulation blowers. The top section contains the ducting system for the exhaust. This is the other end of the fabric through which the fabric is coming out, dried fabric. You can able to see the fumes of it. This is actually because of the leakage problem over here. The blower locations are not appropriately designed, and because of that fumes are coming out. Now this fabric is going to be stored appropriately, and then maybe if it is finished, then it may go for garmenting, or if it is going to be coloring and all it is required, then it will go for the color. So Stenter machine, you might have got the idea. Now I will go to the PPTs. Hopefully my PPTs are going to be visible now. This is the now you can able to understand any physical thing available for the analysis point of view. We wanted to make its diagram sketch, right? So same Stenter we are diagrammatically representing in this particular form. Suppose this is going to be the inlet of the fabric. This is the center two lines with the arrows up and down in between. This is shown as the fabric coming into the center machine. So this whole part is going to be the part of the center machine. This is inlet side, this is outlet side. Then the lines shown over here is nothing but not a physical boundary, but it is going to be the boundaries made for the purpose of analysis as well as from the design of the system. So each section is called as the chamber. So chamber, though we are saying it is not a physically separating unit, each chamber contains the oil heat exchanger where the hot oil is coming, and the hot air which is going to be recirculated through each to increase its temperature, and later on by using the duct it is appropriately going to be blowing on the fabric. So this is going to be the internal structure of the single chamber. This is going to be the hot air heater, maybe basically using the thermic oil. If it is gas fired, direct fired, as Mr. Parikh sir said, then here there is going to be a gas nozzles which are going to be heating the air, whatever is going to be passed over here. And this is the electric motor. This is blower part. Blower is sucking the air. So this is going to be the blower. Blower is going to suck the air and it is going to be blown over the fabric shown here in the red color through these nozzles. Nozzles are over here from both the sides, top and bottom side of the fabric. So hot air, when it is going to be blown on the fabric, water is going to be evaporated. After drying play takes place, the temperature of the fabric is going to be increased for the sizing and desizing, as well as the color settling or dye fixation purpose. The temperature of the fabric requirement is going to be quite higher, maybe around 130 degrees Celsius or 150 degrees Celsius, based on the type of the fabric already discussed. So that temperature is going to be achieved in the center this fabric because of the heating of the hot air. Now the partially whatever air coming out from the fabric, it is recirculated back through the oil heater and partially going out through exhaust duct. Remember here, complete air cannot be possible to recirculate over here. This is mainly because of the constraint from the point of building the moisture. Otherwise, drying cannot be possible. Next, we'll move towards the model side. So you got the idea. There is going to be the nozzles. This is the fabric part. Oil heater is going to be there. We have divided this particular section into a multiple control volumes, and we are going to apply mass balance, energy balance equations to the entire system, as well as each control volume considered over here. And from the point of view of analysis, what is the advantages of this, particularly the benchmarking we have discussed over here? I'm not going much detail about it. This model, we have certain assumptions. fabric is considered as homogeneous along the moisture migration direction, that is the direction of movement of the fabric. The drying process is carried out at steady state, and the temperature, humidity, and other properties of the drying air and fabric are constant with time at a particular location in the stenter. There are so many other assumptions also. This is remember, assumptions which are appropriate and practical will not introduce the error unnecessarily. Definitely, if you are assuming it, it is moving you away from the reality. But if your assumptions are practical enough, then the error introduced is not very significant. It is very less, and because of that, the results whatever you are going to get is equally applicable from the practical point of view also. So always assumptions are not bad. Okay, coming towards the model formation, the mass whatever is coming in from all the sources equal to the mass going out in this particular stenter. If you are talking about, there is going to be the inlet of fabric, inlet of air, then inlet of thermal energy, or maybe hot oil. Hope my PPTs are visible to you. If any issue is there, please let me know. Okay, general form of the energy balance equation with explicit representation of energy loss term for a steady state is given as the mass into the enthalpy of that particular stream equal to the mass of the particular stream going out multiplied by the respective enthalpy, or energy whatever is coming in equal to the energy going out. In that, it is also including the losses. So Q losses, though we have written here explicitly, that is not required. This is the diagram shown over here, especially as a control volume to simplify the things. Remember here, when we are considering the stenter, then there are only the opening at inlet and outlet, and there's going to be the exhaust of the air going out from the top portion, where there is going to be the fan. We can call it an exhaust blower for that. So the oil, this is the oil heat exchanger. Oil, hot oil is coming in, and cold oil is going back to the return oil. Then air is going to be blown on this fabric, this heat exchanger, which is going to be heated, and this hot air, whatever you are going to get, is going to be blown on the fabric through a nozzle. The air, whatever is coming out from the fabric, is partially recirculated back into the heat exchanger, partially is taken by the adjacent chamber, and remaining is going to be exhausted into the atmosphere to reduce the built-in moisture. Moisture should not increase than the permissible limit, otherwise drying is not possible. The similar way, the second also, the process is going to be taking place till the last chamber. Generally, there are going to be small 3 chambers stenter machine to the large 9 to 10 chambers. 9 to 10 chambers means 40 to 50 meters length. It is actually the very huge device, if you see, and a lot of noise is coming over there. Normal people cannot stand over there. Temperature is also more than 50 degrees Celsius, you can say. So ventilation not possible, and you have to just bear it. So from this diagram, we are writing the mass balance equation, which is coming in this particular form, and then subsequently we are writing it. with some notations and substitution. Here you are parallelly learning from the physical situation how the diagram is made, and after making the diagram with use of the fundamental equation, how the mathematical model is going to be made for a particular system. Remember here, the mathematical model is an important aspect to analyze any system. So mathematical model is based on the fundamental equations, and for that purpose you have to study the physics of the system. This is the mass balance equation. Similarly, we can write down the energy balance equation also. This is the energy balance equation. Energy, whatever is coming in, equal to energy going out. For the fabric, energy coming in this diagram, if you see, then energy coming in is through the fabric where it is coming in. Then the hot oil is bringing in the energy. Pressure is coming with certain energy. So these are the major source of energy coming in. If you are talking about the energy out, then energy out is going to be the hot oil out, then exhaust air out, then there is going to be the heat loss from the center wall. Please tell me whether I am audible and going perfectly. If any problem is there, issue is there, please discuss with me through the chat box, that question box. Okay, I will move towards the next slide. Now, first two chambers, this is the energy analysis is shown. Basically, energy coming with the hot oil is here. Then this is the energy going to be carried by the hot air. This is the energy is coming with the fabric, and this is the energy going out with the exhaust air. Similarly, this is the energy going out with the exhaust oil, outlet oil. Then this is the energy going out with the exhaust air evaporation. Then energy out with the fabric is also given over here. In addition to, we have considered the losses. Then in that losses, there's going to be wall loss, leakage loss, and evaporation, exhaust air. This is basically the internals of the Stenter machines shown from the point of view of understanding the minute particles and control volumes. The first control volume we can consider over here as a entire chamber as a control volume. Then second control volume we can consider as a oil heater. Then third control volume we have considered as a exhaust circulation blower. The circulation blower is going to add some energy where the air taken from the atmosphere is going to be mixed. Then fourth control volume, we are going to talk about the fabric, which is going to be blowing on the, which is going to be dried in a particular chamber. Then fifth, we can have entire Stenter machine including the exhaust as a control volume. And the 6th, we can have only the exhaust blower as a control volume, and according to that we can write down the equations. We have the mass and energy balance, one each equation. So 6 control volume, which we are going to have mainly 6 into 2, that is 12 mass balance and energy balance equations. With that we have certain property data and all that. So combinedly putting all that, we are getting a mathematical model of the Stenter machine. This is basically the mixing process. This is done for the control volume 2 and 3. This is the equation for control volume flow. This is for 5U. This is the property relations derived, which is used in this case. This is a similar case. We are calculating how much energy is required for the evaporation. From this, we can analyze the equations and determine the energy required in the Stenter machine. And specific energy consumption, one of the parameter which we are using. Specific energy consumption is nothing but the energy consumption or energy required per unit some quantity, and that quantity can be taken out as per your analysis. In this case, we have considered per kg of water evaporated, and another we have considered per kg of fabric also, but per kg of water evaporated is going to have good representation, and it is going to be comparing two processes because of the common scale. It is going to be easy. The next performance indicator we are using at the energy efficiency index, which is very important. Remember here, it is the value of the energy efficiency index 1 is best, and as the number increases, the performance of the Stenter machine deteriorates. Expected value is going to be 1.5 around. If it is going to be higher than that, then we can say that the energy improvement scope is present, and we can go for the energy audit. After the performance parameters, here we are talking about the representation of energy consumption for the Stenter machine. Remember here, this is going to be considered as the energy at inlet. The hot oil energy coming is around 4 to 6%. The maximum energy is going to be recirculated back into the Stenter machine by the recirculation blower. Then atmosphere here going to carry certain amount of energy, but this energy is not going to be useful as such because it is not having any potential. The fabric is also coming with certain energy, and this is going to be the energy present at the inlet of the Stenter. That is what we can say. Then what way the energy losses taking place, that we can discuss. This is going to be the other losses in the Stenter, and 1 to 4% are going to be exhaust losses. Drying fabric is going to be having the losses, energy in the fabric contains around 0.2 to 0.4%, and recirculation energy is going to be from 93 to 96%. Remember here, the Stenter machine is the machine which is used at very high recirculation ratio, around 99%. Right, and because of that, the recirculation ratio is going to be quite high. 93 to 96% recirculation in this particular case we are obtaining. So after the energy flow in the Stenter machine, heating of the inlet atmosphere here, and okay, this is not required. Exit fabric losses, which we have already told you, that is we have tried to determine. I will go from the literature example. This is the data related to the Stenter is given. What is the data? The inlet temperature of the conveyor Stenter machine. Here they are talking about the conveyor belt dryers, but it is basically the Stenter machines. Hot oil is entering at this particular temperature, going out at this temperature with specific enthalpy at this case, and mass in kg per second is given over here. The temperature of the oil is going to be 240 degrees Celsius. Then water inlet with the fabric, water outlet with the fabric, fabric inlet and fabric outlet temperatures. So all this data is given. And basically what we have to do is we have to determine what is going to be the energy consumption of the Stenter machine. Blower also consuming a lot of energy, and air circulating blower consumes around 60 kilowatt of energy, and exhaust blower requires 5 kilowatt of energy, 5 kilowatt. For this particular case, cotton fabric is used, and for that we got the specific energy consumption as conveyor belt is close to 5,000. For the Stenter machine 1, it is going to be 3,500, and Stenter machine 2, it is going to be 4.3. And in terms of EI, if you consider, then it is 1.84. Then for the second Stenter machine with the improved property, the Stenter machine is going to be 1.36. Then second Stenter machine, the EI is going to be 1.57. What I said is the lower value close to the 1 is going to be preferred. Less than 1 it is not possible, because the energy sent into the Stenter machine is all we have considered over there, utilized somewhere. This is the second example. Similarly, data is available for the second example. In this case, fabric width and fabric speed, outlet moisture, inlet moisture, and number of chambers are given. Number of chambers are given in previous problem also. You got the results table over here. What is the result table in this case? The QW operation, what is going to be the mass of water, energy required per kg of evaporation of water in kilojoule per kg second. Unit is in watt. Specific energy consumption kilojoule per kg of water operated. It is coming around 5.15 kg per kg of water vapor. Important thing over here, it is going to be the EI is 1.92, which is quite higher. The practical value of this 1.5, we are able to get it from the survey, whatever we have done. So if it is close to 1.5, we can say that the Stenter machine is more or less it's consuming lesser amount of energy. Then we'll move to the field study. Total number of stenters we have considered over here around 50 manufacturers. Most of the Indian manufacturing stenters are considered in addition to few foreign stenters. Yuva, Buckner, then Aisung, these are all stenters from outside of the India. That also we try to cover in this case. Our approach is to find out the where energy is going and is there any possibility of saving the energy. This particular file is used to show the location of the stent instruments which we are using it for the data collection purpose. This is the slide taken from Buckner's website, I think so, and they have shown where the Stenter machine sensors are going to be there. In that, it is fully automatic, so very less human interference is required in this particular type of Stenter. However, its cost is also 3 times of Indian manufacturers. Now, these are the instruments which we have used. Moisture content at the exit of the fabric, we are trying to measure inlet and outlet moistures in the fabric. For that, we are taking out the samples, and in a mantra, day before yesterday in the laboratory setup, you have seen the facility available over there. There, they are cutting the sample appropriately to measure the GSM, gram per meter, grams per meter appropriately. Grams per meter is one of the important unit for the point of view of weight of the fabric. So the inlet and outlet moisture from the weight of the fabric also can be calculated and determined, but precision data, precision weighing balance is required for it. Then air circulating power, power quality analyzer we have, that is used for the appropriate purpose. Then power exhaust blower, atmospheric temperature and humidity measurement can be appropriately carried out. Then wall temperatures can be used to determine the wall heat transfer from the Stenter machine. So list is going on. A few instrument photographs are shown over here with their specifications and how they are mounted in the Stenter. These are the samples connected to measure the GSM of the fabric. Remember here how higher the GSM, the thicker the fabric and heavier it is going to be. The thinner the fabric, GSM is going to be lower. So per meter square, what is the weight of the fabric is going to be given by the GSM of the fabric. So these are the at the outlet moisture content in the Stenter machine is shown by this particular device. This is measuring the room temperature, humidity and moisture temperature. This is the screen of the Stenter machine control system. This is something related to the energy measurement, energy power analyzer which is available with the mantra is used for the recording and analyzing of the data related to the power. Okay, with this, I come to the end of the field study. Then whatever the data we have used, we put it in a appropriate way, and we wanted to analyze it. So in a percentage form, the energy, whatever is available in the center, how it is going to be distributed is shown over here. And the majority energy is going to be used for the drying. Then there's going to be certain amount of energy which is going to be carried out for the purpose carried by the fabric. Then these are going to be represented by the wall loss. This is going to be the energy content, content in the pressure, and these are going to be the exhaust losses. Here, three processes mainly carried out in the Stenter, that is dye heat setting, finishing, and heat setting. Finishing operation is basically the last operation before the fabric is going to be going for open sale in the market. If you compare over here, then dry heat setting basically is required a larger amount of energy. The energy losses in that case is going to be higher because of higher temperature. And finishing, the energy losses are going to be minimum. And heat setting, which is in between the finishing and dry heat setting. This is based on the Indian, Korean, and German Stenter. Whatever the analysis which we have done it from the energy point of view. So this is the energy mainly required for the drying operation. Highest energy shown in the Korean Stenter, then German Stenter. Is a minimum energy, then Indian Stenter. So first energy requirement is higher in Korean, then Indian, and then for the German Stenter. If you are talking about a fabric energy losses, then these are almost similar. Then Q wall loss, if you consider, then German Stenter Q wall loss are minimum, and Korean Stenter, it is going to be twice of the German, and India Stenter machines, the wall loss are very high. Then this Q pressure is amount of pressure taken in is higher in the German Stenter, then Korean and Indian Stenter lower. Actually, the exhaust on most of the Indian Stenter, they are keeping low. Very open, very less amount. So very less area is going to be open for the exhaust duct. Remember here, the exhaust duct controls the how much amount of fresh air is going to be taken in, and it helps to keep the Stenter machine at optimal level of humidity, so that your drying process is going to be effective. If exhaust is not operated properly, then it affects whole drying process and the overall heat transfer coefficient, which is important parameter in the convective heat transfer, which is going to be missed. This is typically the graph Q required, how much amount of heat is required in actual case versus humidity ratio. If you see, then as the trend over here, it is going to be not much clear, but what theoretical analysis says that if you are going to be somewhere at 0.1, this is the humidity ratio in exhaust moisture, that means in the Stenter. So if you are at this particular location, then energy consumption is specific energy consumption is going to be lower. You can able to understand maximum Stenters are running in this particular region. It indicates that the operation of the Stenter is not in the economic zone, but it is going to be in uneconomical zone from the energy point of view. And that is one of the reason why the Indian Stenters are these dyeing and printing processes. Stenter machines are why it is inefficient. So to keep this at 0.1 moisture around that requires to have an automatic control system, which is missing. So this is one of the important conclusion we are drawing from our study. We are saying most of the Stenters they are not operated at optimal condition. Whatever may be the reason, operator is not skilled or system is not possible to run. In that case, maybe they wanted to have high production rate and all that. But because of that, there is going to be energy penalty. Energy penalty again results in the generation of increased CO2. So global warming potential is increasing. Green footprint of the product is again reducing. To avoid all these things, the best approach is make some system such a way that Stenter is always going to be run in economical zone. This when I'm going to share the next slide, then in that it is going to be quite clear. Here we are talking about the EI versus the humidity ratio is on the x-axis and EI energy efficiency index on the y-axis. So here you are going to get the trend as the humidity is going to be exhaust air humidity or Stenter humidity is increasing, your EI is reducing. In this EI, the lowest value is going to be considered as the best. Highest means you are moving away from the economical point of view, and your energy consumption is going to be increased, right? So then y-axis, it is shown by the blue color as Q actual in kilowatt. So Q actual and energy efficiency index, you can able to compare. The Stenters which are operated in this particular zone is having a higher EI, means they are not efficiently working. Stenters which are working in this region is having a lower EI, means they are working efficiently. Efficiently means their energy consumption is comparatively lower, but there might be still scope to reduce their EI value. Remember here, right? Then specific energy consumption per kg of water evaporation. This is also giving a similar trend. These are the outliers which may be coming over here because of the operation of Stenter may not be proper, or there might be the data loss, right? But this is the data which is going to be useful. If you see the trend, then similar trend is also observed over here, which is in the last slide. As specific energy consumption, the humidity ratio is increasing, your specific energy consumption is also reducing, or your Stenter is going to be more economic from the energy point of view, right? So the economic operation of the Stenter machine range is this, and in that particular range, the Stenter machine has to be run, right? So most of the operation in India's scenario is carried out in the not economical zone, but in a somewhere operation problems are going to be there. We have carried out the special study of comparison of US Stenter with Indian Stenter. Indian Stenter, especially the manufacturer's name we cannot display it because of our agreement with them. But the Stenter machine, what we are taken from the Indian manufacturer, it is also a good one among the manufacturers. So with that, if we are comparing, we'll come to know where the possibility of improvement is going to be there. This is the data whatever we have collected for the Indian and US Stenter, which is South Korea based company. Pressure, it's going to be 42.5 degrees Celsius temperature, 20% relative humidity, and these are the exhaust gas data. DBT, RH is given, and flow rate. These are all measured data. In the Indian Stenter, there are two exhausts. In Indian Stenter, there is going to be one more chamber. So if I'm not wrong, then I think I remember rightly, then Indian Stenter number of chambers are going to be 9, and then UA there's going to be 8 chambers. If you compare the energy flow diagram, then from that you will be able to understand the in and outs of the energy. The thermic coil energy is going to be contained this much, and it is going to be given to the Stenter. And the pressure energy content is given over here. So this is going to be the energy present at the inlet, and this is the energy present at the outlet of the Stenter. Energy at the outlet, if you are talking about, the exhaust content highest amount of energy because evaporation energy is also carried by the exhaust. And there is going to be some wall losses, and fabric and outlet energy is going to be this much. This energy requirement is going to be 570 kilowatt. This is kilocalorie per kg of water. While writing the unit, it is not appropriate. It's a kg of water it has to be. And the energy supplied is going to be around 900. So 570 plus 9 minus 900, there is going to be huge difference, and this is especially maintained to have the for the compensating various losses, including the wall loss and other things. This is another way of showing the energy distribution. This is the same data graphically represented for the Indian Stenter. If you see, the energy required is 570. Here, energy required is also around 570, but supplied energy is going to be 172. On the other hand, here supplied energy is going to be just 900. So energy consumption point of view, if you're talking about, then we are lacking so many places, and that is what we wanted to analyze it. Drying rate, if you are talking about Viva Stenter, this is for the Indian Stenter. Then we are considering the EI index versus the average versus drying rate of the Stenter machine. This slide is talking about a circulation blower, how much energy is required, and blower exhaust energy. Circulation here, blower energy is going to be very high for the Indian Stenter comparatively the Korean Stenter. Similarly for the exhaust also, in Indian Stenter there are two exhausts on another side. South Korean there is going to be only one exhaust. Further, the Circulation blower quantity is going to be huge. Comparison of energy index EI value, if you say, then this is going to be huge difference over here seen in the graph. Here its value is 1.8, on the other hand 1.67. Now I'm just on the side of closing of my presentation. Overall conclusions in this particular case. If you are talking about the energy requirement in the US Stenter is going to be a little bit higher than the Indian, but energy supplied is going to be higher in the Indian Stenter than the UA. Similarly, the Pacific energy consumption, if you see here, the Pacific energy consumption per kg of water is lower for US Stenter than the Indian Stenter. Here, the energy utilization also, if you see, the energy utilization is higher in the US Stenter than the Indian Stenter. The number of blowers, both circulation and exhaust, are lower in a UVA machine than the Indian machines. Therefore, the energy consumption is also significantly lower for the same machine as compared to others. Further study can be taken up to reduce the number of blowers without affecting the quality of the product and applicability of the machines. These are, there is need to perform the thorough evaluation of blowers to understand the current scenario of the machine. So CFD work can be taken out appropriately. The wall losses per unit area for UVA machines are lower. Even the hot air temperature are higher. That is, the hot air supplied for the UVA Stenter is 150 against 130 for the Indian Stenter. This indicates that there is a scope to reduce the wall losses in the Indian Stenter machine. For this current case, insulation material and the thickness can also be analyzed, and based on it will be decided whether to change the material or increase the thickness of the insulating material. So to appropriately reduce the heat losses from the wall, the insulation can be changed, or the thickness of the insulation can be increased. Appropriately need to be decided based on the cost. The exhaust losses can be further reduced in the Indian Stenter by adjusting the exhaust blower gas flow rate appropriately in the optimal range by adjusting the exhaust gas humidity in the range of 0.1 to 0.15, which is already I discussed. The overall losses per unit for the UVA machines are lower than the hot air temperatures. Okay, this is we already discussed. Possibility of automatic VFD drive may be explored, which is currently not automatic, but just to change the speed of the exhaust blower in case of Indian Stenter machines. Overall, after implementation of above suggestions, 2 to 4, performance may be improved by 10 to 15% compared to the current performance. Further, the study of circulation and exhaust blowers may be given significantly high savings if compared to UVA Stenter. In long-term research decision, design of the oil heater, design of nozzle with air passages need to be verified using latest computational fluid dynamics software for optimal pressure drop and maximum heat transfer capability. So the overall remark I wanted to put as if you are talking about the any device, first of all, very closely observe the system, try to make the sketch out of it. Then based on the fundamental law, you can able to formulate the mathematical model of it, and that mathematical model can be analyzed and some results can be produced. That results can be appropriately discussed and justified. So the discussion of the results is one of the important aspects which need to be carried out. So energy benchmarking is one of the proven tool we can say for the industry to save the energy, and it has to be used so many places. Okay, so one of the important contribution from this project is the Stenter machine, which is highly energy intensive in textile industry, for which we can able to provide the star rating. And that particular process in the that particular work is in the process. We have to go for more 5 to 10 stenters, but because of the lockdown, our work is completely stopped. After this lockdown is get to open and industry is going to be very important. Then lockdown is open, we can go to start that work. Second important contribution about this particular project is going to be the scope for the energy recovery in the Stenter machine. The Indian scenario, the first and foremost thing is we have to look in the operation. Our operations are inefficient, and our objective is first should be to go for the efficient operation of the process. Maybe the operators are not trained, or they are not educated enough, or they are not aware of it. But for that point of view, we can have some sort of training sessions, and we have to train them to make the Stenter machine operation in the economical range. The third suggestion, what I wanted to say, is related to the further improvement. We can have definitely the closed loop control system design for the Stenter machine, so that the operators involvement is going to be as minimum as possible from the efficient operating point of view. Then the latest tools of the computational fluid dynamics definitely useful for the small and medium scale industry to design the inside air flows and heat transfer capability, so that the energy transfer is going to be very high. And because of energy transfer is high, the operation of the Stenter is going to be improved, and energy saving scope is going to be generated over there. So with this, I think I come to the end of my presentation. Before going for it, I wanted to acknowledge the people who have directly, indirectly helped. First of all, Ministry of Textile, Government of India, who sponsored this project. Our industry partner, Vallabhbhai Mungukia, Yamuna Machine Works, which is at Wapi. They have supported wholeheartedly for this particular project. Then, of course, the entire team of the Mantra, including Dr. S.K. Basu, who is the director of Mantra. Then the R&D head, Mr. M.G. Parikh, the assistant director, Dr. Shamal Maiti, our project staff, Mr. Rahul Patel. From the SVNIT side, I acknowledge the efforts put by Mr. Nikunj Patel, who is also a faculty in SVNIT as well as the PhD working on this particular problem for his PhD work. Another my PhD student, Mr. Sanjay Patel, and of course my friends, colleagues from the SVNIT who directly, indirectly help to carry out this work. So I thanks all the people directly, indirectly who helped me. Last but not least, if you really think the environment is less important than the economy, because when it is going to become as energy saving, we always think of time saving or some sort of monetary benefit, then my suggestion is going to be very simple. Try holding your breath while you count your money. And that is the important of air, which is we are freely breathing. If this air is get polluted, then where is the life? So pollution, if you wanted to stop, then we have to begin from the thoughts. Pure and positive thoughts will eliminate all types of pollution and we can live the life happily. Thank you. Thank you. If you have any question, suggestion, please let me know. I will try my best to answer the queries raised by the participant. Yeah, I'm now able to see the question box also. Okay, if anybody having any question, any doubt, please let me know in the question box. You can type it in the question box. Somebody, I think one of the presentation asked about the thermic oil, what type of thermic oil. Remember, there are natural synthetic thermic oils as well as natural oils, also mineral oils. Synthetic oils are able to get higher temperature. In the Stenter machine, the temperature we require around 200 degree. The air temperature varies from 180 to 200 degrees Celsius, and oil temperature is going to be maximum 240 to 220 degrees Celsius. So at any case, we are not going to go higher than 270 degrees Celsius. So Solutia is one of the thermic oil based company, and their products are sold by the trade name as Solutia. Solutia 55 generally is falls in that particular temperature range, which is used in the textile industry for the thermic oil heaters. Still, if you have any question, any query, please let me know. Otherwise, I will wind up this particular session. Dr. Maiti. Hello.
Yes, sir.
Sir, if you have anything to say.
Sir, Mr. Parikh will conclude the session.
Yeah, Parikh sir, but it's not visible over here.
It is.
No, I am there.
Acha,
Hello.
okay. Sorry, sir.
I'm using
Okay. You are with
Dr.
Dr. Blakey. So, okay,
Yeah,
sir.
yeah.
You give your comments and some suggestions. If any.
Yes.
Yes.
So, thank you, Dr. Bade. And it was a nice presentation. What I would like to add something to what you have said. I will give you the background of this project work. Particularly, Stenter is the main machine of any process house, which contributes about 20% of total energy consumed. And so it's a very important machine. But it is also a complex machine because the fabric is continuously entering in a wet state, and then you have to dry it. There are so many chambers, and hot air is circulating in each chamber. There are, heat losses due to wall, and humidity is generated, which has to be taken out. So it is, and I tell you, not much work was done before we started this. This is one of its kind. The study is one of its kind, and the outcome will definitely benefit the industry as well as it will be helpful to the government, because the performance of Stenter will ultimately decide the performance of a process house, energy performance. So this project, we are also trying to cover as much as 35 Stenters, and we are also trying to cover different varieties. I mean, synthetic fiber fabrics, which are prevalent in Surat and other decentralized cluster, is a very lightweight variety, and polyester is a hydrophobic fiber. So the moisture content of the fabric is not that. But when we go for cotton, cotton has got 7 to 8% of the moisture regain. So the energy consumption in case of cotton is much more than the polyester. So we are trying to cover cotton as well as polyester and blended fabrics, and about 35 Stenters. So I hope that the outcome will be very helpful to the industry as well as the government. Government, why? Because government can now decide based on this benchmarking, they can grade, the star rating may be given, and then they may decide on a policy on subsidy or something like that, or whether they have to give some incentive to a better performing Stenter. So thank you, Professor Bade. You have explained this in a very nice manner, and thank you very much to all the attendees. I thank everybody from Mantra as well as from SVNIT side who have helped in this project. So thank you.
Thank you very much, sir. So participants, last announcement. We can have a test at 4 o'clock. It's going to start. We are going to share the link through emails, and also it is kept in the chat box over here at 4 o'clock sharp. We are going to have half an hour for the quiz, and after 4 to 4:30. So 4:30 we can start valedictory session, and in that you have to share your views. If anybody wanted to give any comment or anything, right? So thanks everybody being over here, and with this I end my session.